Thank you. Good afternoon. This talk is about some of the work that the CSIR is doing in the area of computer vision, and particularly computer vision for an autonomous mobile robot. What I intend to do is first look at vision systems in general, then computer vision in the context of a mobile machine, then look at an example here of autonomous exploration and mapping. This is some of the work that's being done at the CSIR, and then some applications. If you think about vision systems in general, a great example is the human vision system. We have two primary vision sensors. Whoop, I hit the wrong button there. Nice. We have two primary vision sensors, which are our eyes, and of course the central nervous system, or the brain, which does the analysis and interpretation of that visual information. So light entering from the environment finds some photosensitive receptors in the eye. It's converted into a signal then, which is propagated along neural pathways down to an interpretation center here in the occipital lobe, and that's where that analysis and interpretation is done. And the point of bringing this up is simply to say that if you're talking about a vision system, it's not just the sensors, it's actually the sensors as well as the processing centers. And we will see that when we look at computer vision as well. There's an exact kind of parallel. Computer vision system would have one or more vision sensors. It would have then a computer which handles the analysis and interpretation of the data. But you can see a parallel in that setup. So sensors would receive or would provide the data to the computer. That is our computer vision system. And then subsequent to that, we could do some decision processing and display from the analysis, so feature extraction or region identification that's being done by the computer. Okay, so what kind of sensors are used then in computer vision? And what we find is that there are a lot of cameras, very commonly used cameras. A monocular camera or a single camera can be used. You can also think about a stereo pair of cameras. This is basically two cameras with a fixed, or let's say a known separation between them. And if you think about a human visual system, we use two eyes, we get some depth perception. You can get the same kind of thing with this stereo pair. We can also have an omnidirectional camera where a 360-degree plane is the entry point for light. And that light then is reflected from this mirror up into the camera system. But that allows an entire 360-degree to be represented in a single image. Laser scanners as well are very common in computer vision. So the laser would put out a light beam, and it would be reflected from an object in the environment, measure the time of that delay, the time delay from light reaching the object and being returned, and you can determine then how far away an object is from the laser scanner. Similarly, we could have sonar as well. So this is an example of some sonar sensors here. Putting out a sound wave, receiving the sound wave, and the same kind of idea, you can find out where an object is in the environment. If we think about computer vision in the context of a mobile machine, some good examples, or a great way to look at this is just through a couple of examples. So one of them would be the NASA Curiosity rover. You may know that this rover is currently active on the planet Mars. It was developed by the United States National Aeronautics and Space Administration. And it's actually quite a large robot. The wheels are 0.5 meter in diameter, and the height of this robot is 2.2 meters. The computer vision components are on this head, which stands on a mast. And if we look at that, on the right-hand image here, we can see some of the vision components. Immediately you can see on the left here a camera. This is a telephoto lens. Another camera here on the right is a kind of a medium angle camera. These are mainly for taking images, the images that you would see if you went to the website. were taken from these two cameras. The navigation part of it is done by these nav cams, one on the left here and one on the right. And these ones actually are dedicated to the navigation of the robot. We can also see that, so this is a stereo pair up top here. There's a redundant pair down below. And each of those feed a separate computer. So what we have here is a computer vision system based on cameras with full redundancy. Another very good example is the Google self-driving car. Most people have probably heard of this, at least. This has been extensively tested in the United States. Basically, lasers, radars, cameras, and proprietary software form the computer vision system here. And what you can see is a lot of sensors. And you can think of what this environment of this device is urban environments. So it's an autonomous vehicle that can self-drive through urban environments. These sensors give it about a 200-meter, roughly, radius of sensing range. And it has to pick up things like, obviously, fixed objects, moving objects, pedestrians, cyclists, other cars, road markings, and traffic lights. So there's a lot that's involved in that. Availability of this, roughly 2020, is projected. And this is well within, the next few years, so we can start to think that maybe we're going to have some autonomous vehicles in our life, in our regular daily life, through vehicles like this. Okay, if we just sort of try to generalize on some of the system hardware, and here we're talking about ground vehicles, a robot system would typically have wheels and a frame. Electric motors would drive the wheels, and batteries would provide the energy source. Internal sensors, we'd have odometry. We can measure wheel motion and get an estimate of where the robot is if we just measure how many times the wheels have rotated. That's one way. So this would be internal to the platform. As well, an inertial measurement unit will give us linear acceleration and rotational velocities. Now these, in this picture here, are development platforms which are owned by the CSIR. And I should also say that this really, we're talking here about some ground vehicles, and I know there's other work being done at the CSIR in terms of water-based vehicles and also in terms of aerial vehicles. So this is just a subset of the kind of work that CSIR does in robotics. But speaking about the system hardware, also system software for an autonomous machine, and this is a very simplified block diagram here. But the vision components in that would be the sensors. Okay, each sensor would have some kind of a software element to it to couple the data from the sensor into the rest of the software system. That kind of information, the vision information, could be provided to a collision detector, and this would look for objects or obstacles directly in the path of travel. The idea there would be to either stop to avoid a collision or find a way around that obstacle. The vision information is also used in map formation, and this is a very key component of the vision system, which we're going to look at a little bit more. But when you have a map, you can do a kind of planning operation, and you can also drive the robot according to that plan to get from point A to point B. But let's look a little more at this map formation. This is a computer vision algorithm for map formation called simultaneous localization and mapping, or SLAM for short. And in particular, this is a scan matching method. If our robot sits here at point A in this environment, and let's say it's facing in this direction of this red arrow, and let's say it performs a 360-degree scan, and it finds in that scan these walls, these blue walls. Of course, it can't see around corners, so there's some limit to where it can see. And so we get a partial representation of the environment. If we move the robot, we can then do another scan. Here it is at point B. Again, it's facing in the direction of this red arrow. and it scans in 360 around itself, and it finds some walls. Again, it can't see around corners, so there's some limit. We have a partial representation of the environment. And what we'd like to do really is put these together and get a better map from that, which we can do because, assuming we haven't moved too far, there's some overlap between these two scans. So if we can match those, we can do a couple of things here. We can first get a better map. Now we have, in this case, a full view of this environment. Our position at point A, our position at point B are now related. So the transformation that we get by this scan matching, first of all, develops the map and also gives the robot location within the map. So that's an example of a computer vision algorithm, simultaneous localization and mapping. Now I'd like to give an example here of some of the work being done at the CSIR in this autonomous exploration and mapping. I should also say that the CSIR is also active in manipulation and mobile manipulation, so the robotic arms and the picking and moving of objects. But here we're just going to look at autonomous exploration and mapping. The robot platform in this case is a PackBot 510, which is manufactured by iRobot Corporation of USA. We have put on this a sensor mounted here, and in the payload bay we have a computer, and so that's our computer vision system. Here's the sensor, there's a wire which carries the information down to the computer, and that's our computer vision system. If you look at the front of this, we see some cameras. There's a head cam here and another camera down lower. Okay, so two cameras in particular. There are more on this platform, but we have one on the head cam here and one a little bit down below. And those are used for feedback to an operator. If we take a look at the vision sensor itself, it's a 3D laser scanner, and it has 32 laser beams. They come out of this window, basically at different angles, and then the top of this scanner, top of this sensor is actually rotated. And so that gives you a 360-degree scan of these laser beams. If we put this sensor about 1 meter off the floor in this environment shown in the lower image here, what we would get then is what's in the upper image here. This is called a point cloud. So every place in that environment where there was a return from a laser beam, we would get then a point in this representation. So if we look at this, we can see a couple of chairs in this environment. We can see the backs of these chairs in this point cloud. Also, the support structures for these tables are also there. You can see them on the left here and at the back. The two walls, the one at the back and the one at the right, are also represented there. And if you look closely, there's a computer screen, which is also represented in there. And not to mention the floor here as well. These purple points are reflections from the floor itself. So this is the kind of information that will go from this sensor down to the computer in our system. Okay, we also have an operator console for this whole system. We see I mentioned two cameras from the robot. These are on the left-hand side here. There's the lower camera, which shows a kind of a wide-angle view, and then the head cam. There's also some control here. The operator can control the motion of the robot, put it into autonomous mode, semi-autonomous, or manual drive. And on the right here at the bottom, we have the map produced by this robot. And you can see it's a three-dimensional map. The representation of the robot within this environment is made by this little white identifier here. And the path that it's traveling is this green line. And what it's done now is it's scanned an environment through many of these scans. It's moved through the environment and scanned it, and this is the result. But what I want to do is show you a video of that, and I'm try it from here. Okay, so this is going to be a video here similar to what you saw in the previous slide. So on the left-hand side here we have the two camera views, and on the right is that computer-generated map. The icon or the representation of the robot is here, this white object, that's our robot, within the context of the environment as it has determined it. The black area is what the robot has determined to be drivable area. The gray is unexplored, so it hasn't been there yet. In terms of the obstacles, the red markings here on the ground plane are indicate obstacle, and the orange around it is a kind of an expansion zone around that obstacle, so a safety zone around it. What we are going to do is go ahead and let it go. We can start, thank you. And this is fully autonomous operation here right now. So this robot is completely on its own. It's deciding where to go, where to explore. What it wants to do is find these areas which are unexplored, move there, scan the area, include that in the map, and keep doing that until it's fully explored the environment. And you can see the video from the robot on the left-hand side here. But the right-hand here is completely computer generated. Okay, now it thinks it's done, but there's actually one more up here. It doesn't think it's done, it's found it. And it's planned a path through these obstacles. To that point, it's going to scan this area, include that in the map, and that should be it for today. Now this is 4 times speed up, I should also say. So this is a 4 times speed up. But you can see as it approaches this goal here, it starts filling in the wall. And when it reaches that point, it will have completed the map. Okay, and so that's our, yeah, that's the completed map there. Can we just put that up again briefly? Okay, going back to this slide, what you saw in the video is the creation of maybe a smaller area than this one. But what you then see is that the 3-dimensional representation of the environment is certainly captured in the map. You can see obstacles that were within the view of the robot. In this case, we can see in this camera view a glass wall here along the left-hand side. That's visible here. There's a desk here on the right, visible over here, and of course the walls along the side. So from these camera images, we can see that, yeah, we have captured that environment. Okay. Okay, that was the video. Yeah. So in terms of applications of this kind of technology, remote reconnaissance is a good application for this. What you're trying to do there is obtain information about a selected area or region from a remote location, so remote reconnaissance. Examples of that would be areas such as public safety or police operation, hazardous materials detection, or military reconnaissance operations. This image on the right is a PackBot robot, the same model as what we just saw in the exploration and mapping example, entering one of the buildings at the Fukushima nuclear disaster area in 2011. Now this is being manually driven, this robot. It's not an autonomous vehicle at this point. But you can see a case like that would be great to have a machine that could give you some kind of remote reconnaissance. Another area is remote inspection. So remote scans of selected structures or materials, and we're looking there for structural integrity or operational status. And remote, yeah, because we're probably going to have a case, or what we're interested in actually are cases where there are hazards or space constraints. So places where it's difficult or dangerous for people to go in are great places for machines like this. Examples there, liquid chemical storage tanks, a nuclear plant or damaged infrastructure. The chemical storage tanks usually find them at ports, so seaports, and they have to be inspected at regular intervals. Typically they have a floating ceiling, so when the tank is emptied, the ceiling is very, very low, so there's space constraints, and so this is also a great application for a robot like this. Summary then. Computer vision, we're talking there about sensors and the hardware and software, the analysis hardware and software. So we're talking about a system, sensors plus the analysis elements. And the autonomous mobile robot, it is, as we've seen, it operates in relatively unconstrained environments. It uses artificial intelligence, so the SLAM algorithm, path planning algorithms like that. and it will control its own motion. So that's what we're talking about there. And in terms of application, we saw exploration and mapping, remote reconnaissance, and remote inspection. These are the kinds of applications that the CSIR is looking at for this kind of technology. Thank you.